For next topic, we will discuss about Cartesian vectors in three-dimensional system. So before we will start, let's have a quick discussion about the right-handed coordinate system. So a right-handed coordinate system will determine the proper placement of the x, y, and z axis in space by following the concept of right-hand rule. So basically, you will use your right hand, as shown here in the figure, to determine the positive directions of the three axes. So for the z-axis, basically you just need to check the direction of your thumb. Then for y-axis, you need to check the direction of your fingers, which is pointing in this one, at this direction. Then for the x-axis is the direction of your palm, which is covered by the fingers in this figure. So that's how you determine the proper placement of x, y, and z-axis. So basically, if you change the direction x, z, y, this one right here does not follow the concept of, or the principle of right-handed coordinate system, because the y and z coordinate axis is interchanged. If you want to interchange it, let's say this is x and y and z. Basically, this is a correct pattern for the right-handed coordinate system, because this one is still following the right-hand rule. If your thumb is pointing in this direction, you can see that your fingers will point here and your palm will point here in this direction. So you can also use, example, if you use this as x, then basically this is y and this is z. So this is still correct. You can still use the right-handed coordinate system in this arrangement of the axis. So it depends on the problem. So next one is the vector A along the presented in the coordinate axis, the three coordinate components. So we have here vector A is directed along its where its components is directed along the positive x, y, and z axis. So to figure it out, because remember that this drawing is a three-dimensional figure, so I always use this technique. I draw a shall we say a solid, a rectangular parallelepiped, which is this one. Just remember, let's say it is a shoebox. Say a shoebox. So the box has always three sides or three dimensions, which is the length, width, and height. So always remember that the dimension of the box, which is the length, width, and height, represents the length or the magnitude of the three components AX, AY, and AZ. So example for AX, this length right here and this one also, this one and this one is the length or the magnitude of AX. For AY, this side right here, this one and this one and this one represents the magnitude of the y component of the vector. Then for z, represents the height, which is measured here and also here, this one and also this one, represents the z component of the vector. So that's how you interpret the figure so that you won't have difficulty, especially if the figure is so many forces are placed later on in our further topics. So you just write or draw a rectangular parallelepiped. So later on, if you practice more and more, you will understand it without drawing the rectangular, the shoebox. Shall we say it's a shoebox? No need to write it if you already master the concept. So where is vector A here, which is the resultant of the three components? Basically, it is measured from this point to this point, which is the one corner to another corner. So, in other cases also, I also use the concept of the triangle law, wherein the components are connected in a head-to-tail manner. So, in this case, example, this one is AX. So, basically, this is AY, which is this one. And AZ is this one, AZ. So, from this point to this point, this is Z, AZ. This point to this point is vector A. So, that's sometimes I will use because this one is still a box. Remember that this is still a box, which is this one. You can use the triangle law also to determine the components and draw it in this manner. So this is another technique that you can use. Another important consideration also is to express the vector A in terms of its vector notation or vector representation. So as you can see here, the same thing to the two-dimensional system. We have the ij for the two-dimensional system. For the three-dimensional system, we just add the third component, which is az, the z component. And we will use k, unit vector k for that particular component. So it will look like this, basically the same. So this is the x, y, and z component of vector A. So same goes by with the two-dimensional system. If the component is, the direction of that component is opposing to that axis, particular axis, let's say for z axis, let's say AZ is going downwards, so this one right here must be negative. So same concept or same principle also apply to both AX and AY. If the direction of that component is opposing to that axis where that component is lying. So next one is how to determine the magnitude of A. So basically, you just calculate the measurement from this point to this point using the components AZ, AX, and AY. So same formula in the solid geometry, which is this one. So the magnitude of A is equals to the square root of the sum of the squares of the three sides of the shoebox. Let's say this is the shoebox. So basically, it is easy to remember because it's somehow the same with Pythagorean theorem. And you just add the third component, AZ. Next is how do we determine or express the components AX, AY, and AZ in terms of its magnitude of the component, or shall we say the magnitude of the vector itself, vector A, and its angle, direction angle. So to do that, we just try to illustrate right triangles that is being formed from the components and the vector A itself. So remember that this triangle right here is a three-dimensional, is coming from a three-dimensional figure. So maybe you are asking how come that this is 90 degrees. Basically, if you are looking on the 2D plane, it is not 90 degrees, obviously. But in three-dimensional figure, if you draw this one, if you are considering the space itself, the three-dimensional space, so this one is a rectangle because this one is a 90-degree corner. So how come? Example, if this one is a door, let's say this is the door. So basically the door is a rectangle with all corners 90 degrees. If you open the door, let's say this is the doorknob, then this is the hinge. This is where the hinge is placed, the hinge on the door. So if you open the door, it will turn out to be like this. So open the door. So this one is the position of the door. So if you open the door, obviously the size or the shape of the door will not change. So basically it's still a rectangle. So that's how you figure it out. So just imagine this figure as a three-dimensional figure. So if this rectangle right here is divided into two right triangles, which is this one, triangle 1 and triangle 2. So that is a right triangle because this one also is a 90-degree angle. So basically this is AZ, which is the adjacent side of alpha, and this one is the hypotenuse because it is opposite to the 90 degrees. So it will look like this. So this is AZ, this is A, and this is gamma. So we will call the angle gamma, which is the angle measured from AZ to A. So this is 90 degrees. So if you use the formula of trigonometry, cosine of gamma is equal to the adjacent AZ divided by A. Same goes by with the other two triangles. So you just draw right triangles. This one is 90 degrees if you imagine this as a three-dimensional figure. And also this one, that is also a 90 degrees if you imagine this as a three-dimensional figure. So if you draw, this will look like this. So this is 90, this is beta, this is AY, and this is A. So cosine of beta equals AY over A. Then for this one, for this triangle, so this is 90, and this is alpha, this is AX, and this is A. Basically, cosine of alpha is equals to AX over A. So that's how you determine the right triangles formed by the components and vector A. So simplifying so that you can have the components, the equations in terms of the components. So we have AX, AY, and AZ. Simplifying the equation, you will get this one. So somehow this formula is the same with the two-dimensional system. If we compare it to the two-dimensional system, so remember we have Fy and we have Fx, and this one is F. So this is x-axis, this is y-axis. So remember the angle of F in terms of x-axis in this figure is alpha. Then the angle of F to the y-axis, which is this one, angle of, we will use beta. So if you solve for Fx and Fy in terms of F and the angles, so you will get Fx equals F cosine alpha and Fy equals F cosine beta. So the only difference between two-dimensional and three-dimensional system is that a two-dimensional system forms a plane, rectangular shape, which is a plane. So therefore, the dimensions of the rectangle is equal to the components Fx and Fy. And for three-dimensional, it forms a shoebox, which is a solid, wherein the dimensions of the shoebox is representing the components x, y, z, ax, ay, az, components of the vector A. Let's also discuss some important formulas that we can use in analyzing three-dimensional vector with components ax, ay, and az. So these are some important formulas that we need to remember. So let's discuss about the vector representation A in terms of its magnitude, which is this one, and in terms of the unit vector lambda. So again, a unit vector, which I didn't explain it on our previous slides. When we say unit vector, it is a vector with magnitude of 1. So a unit vector, basically unit itself, one unit vector with a magnitude of 1. So why is it unit vector is important? Unit vector is used because if this unit vector has the same direction of, let's say, vector A, you just multiply this unit vector to its magnitude to get the vector form of A. So how do we compare that? Let's draw the same vector. Let's say we have this one. If we draw this vector here from here, and these are the components, 3 components, AX, AY, and AZ. So let's call this one unit, and let's call the X component as lambda X, lambda Y, and lambda Z, because lambda, which is the unit vector, has a magnitude of 1. So if we compare these two shoebox, let's say these two shoebox are proportional, meaning the ratios of the sides are proportional to each other, with this other box, this bigger box right here, because this one is a bigger box, we can say that vector A, in terms of its magnitude A, is equals to lambda divided by its magnitude, which is equals to 1. So simplifying this formula, we will get this 1, because 1 will be neglected there. So A vector, which is equals to A times the magnitude, this is the magnitude, then times unit vector lambda. So that's how we come up with this formula. Remember that these two must be proportional, so that their direction is the same. So let's discuss the 3 components, the magnitude of the 3 components, lambda X, lambda Y, and lambda Z. Remember from our previous formula, let's go back here. So this one, so this formula, remember that if we apply this formula here, we have AX equals A cosine theta to the lambda, unit vector lambda. Remember the magnitude of lambda is 1, and its components are lambda X, lambda Y, and lambda Z. So basically, this A right here, A and A here, are replaced by 1, and this AX, AY, and AZ will be replaced by lambda X, lambda Y, and lambda Z. So basically, the formula will look like this. We have 1 here, but we don't need to write it. 1 is the magnitude of lambda, and we have the same angle. Since this vector is the same with this, shall we say this unit vector has the same direction of this vector A, therefore its angle are also the same angles, because they are proportional. Then for the identity, remember vector A is equals to the square root of AX squared plus AY squared plus AZ squared. So since this is, if you use this in this particular figure, the unit vector lambda, this becomes lambda X, lambda Y, and lambda Z, then the magnitude is 1. So this will simplify to this equation. 1 is equals to lambda X squared plus lambda Y squared plus lambda Z squared. Then, if we use this formula now, if we take advantage of this formula, this one, cosine theta is lambda X, cosine beta is lambda Y, cosine gamma is lambda Z. Basically, if we use that in our previous drawing here, we can replace this one with lambda x, this one with lambda y, and this one right here with lambda z, lambda y and lambda x. So ax becomes a lambda x, and all the same with the other formulas. So it will look like this. So that is the magnitude of the components, which is ax, ay, az, in terms of the direction cosines, which is the lambda x, lambda y, lambda z. Remember, always remember the terms. Direction cosines is the components of the unit vector. That is lambda x, lambda y, lambda z, which is the formula is very easy to remember. Then its identity is this one, because unit vector is a vector with magnitude of 1. So let's have an example here. So again and again, please try to solve. Take a pause after you look at the question, then try to solve it on your own first, so that you can check yourself, you can check or you can assess yourself if you have understand it. Then play it after you answer the problem. Then you can compare your answer to my answer and check if you got it right. And better, if you didn't get it right, you can check which part of your solution is not correct. Then you can learn from it. That way, you practice your problem solving skills. So let's have here an example. So from the given figure, so as you can see, we have here force vector, which is 200 newtons, with direction angles alpha for x-axis, and basically this is beta because this is for y-axis, and this is gamma for z-axis, measured from the vector to each coordinate axis. So the question is, letter A, determine the angle alpha. Letter B, determine the vector representation of f, which is basically fxi plus fyj plus fzk. So you just need to determine these three components. Determine its, shall we say, its magnitude, so that you can apply it here. So from the figure, you can see that fx, fy, and fz are positive. This is fx positive, fy is positive, and fz is positive also. Then next one is the corresponding unit vector, lambda. So that is in the form of lambda xi plus lambda yj, because unit vector is also expressed or written in vector form because it is a vector, unit vector. So let's start with problem letter A, the angle alpha. So to determine that angle alpha, we know that there is what we call the, shall we say, the identity for the unit vector. If you could remember this, lambda y squared plus lambda z squared. And this one right here is cosine alpha, cosine beta, and cosine gamma. So we know that we have here beta and gamma. So we don't have alpha. So if we use this formula, we only have one unknown, which is alpha. So let's try this one. So this is the shoebox. If I draw it right, you can, so that you can imagine how the vectors are formed or the components are formed. So let's use the identity. So substituting the formulas, which is lambda x equals cosine alpha, lambda y is cosine beta, and lambda z is cosine gamma. So you will get alpha, which is, if you simplify, you have, because you have here alpha equals arc cos or cosine square root of 1 minus cosine 60 squared minus cosine of 45 squared. So you will get two answers because that is positive and negative. So it will look like this. So the answer of alpha is, we have two answers, 60 and 120. So how do we determine which is the correct answer? So to check that, we just determine if alpha is an acute angle or, shall we say, it's a angle greater than 90 or less than 90. But for this figure, if you don't look at this in a three-dimensional point of view, you might get the answer wrong. So that's why you must understand that this angle right here is an acute angle. So how come is it an acute angle? Let's have a drawing on this side. Say this is the x, z, and y. So we know that fx is in this direction. So this is fz, and this is fy. So the box, you already know what the box is, so it will look like this. So basically f is in this direction, going to the positive x, y, and z axis. So basically, if fx is positive, which is in this direction, we can see that the angle or the direction of f measured from the x-axis is an acute angle, because it is, this point right here is on the right, on this side right here of this plane. This plane, it is not in this side, in the back side of, imagine this as a wall. So in the front of the wall is this one right here, which is this figure, and the back of the wall is this one. So this one is the front of the wall. So this one is 60 degrees. So how come that the answer or the solution will provide us a answer of 120 degrees? That 120 degrees happens if we remove this, we change the direction of fx into negative. So it will look like this one. So this one is fx. The same goes by with fz and fy. So that's how. So basically the f here will look like this one, f. So the measurement will increase. So basically if you draw this on a 2D plane, so this is x and z. So this one right here is f. So this one is fx. So this is the 60 degrees because fx is pointing in this direction, in the positive. But if you point it here, this is fx, the measurement will become 120 degrees. Because if I draw it again, let's erase this one. If this is fx, which is negative, the measurement is like this one. So this is 120 degrees. But fx is not negative. We know that it is positive. So this is the correct dimension or correct answer for alpha. So our final answer will be 60 degrees. So it's a matter of analysis, problem solving skills also. Apply the concepts of mathematics and geometry, especially geometry and trigonometry in this one. So just practice it so that you always remember that. So next one is letter B, the vector representation of f. So you just simply calculate fx, fy, and fz. So the formula is very easy. Fx equals f cosine alpha. Then if you want it fy, then you have beta. And you have fz equals gamma. So you just write it like this one. Oh, basically this is fx. I wrote it wrong. So this is f. This is f. So that is 100 for 60 because we already calculated this one as 60 alpha. And beta, and gamma. So this one here is, all of this is f. So you will have the xyz component. All of them are directed to the positive xyz axis. So therefore, all of them is a positive value. So if you write that in the vector form, so basically this is f in vector form, you just substitute it here, fxi plus fyj plus fzk. So this one will be the answer. Then finally, unit vector, which is lambda. So unit vector lambda has a very simple formula. Remember that a vector equals a times lambda. So we just want to calculate a vector, and we already have this one from part B. A can be calculated using the formula of square root of ax squared plus ay squared plus az squared. So these three values right here, we already have that. So using this formula, unit vector equals a vector, which is, we already have this one, and this one is easy to calculate. So actually, you don't need to calculate a because it's already given 200 newtons. But if you want to check your answer, you try to solve this one using your calculator. So you must derive with the same answer, which is 200 newtons. So that's how you use the formula. So dividing, you will get this answer. How to determine if your answer is correct in the unit vector? You just apply its identity, 0.707 squared. So the answer here, if you calculate that, must be equal to 1. So if it is not equal to 1, then it's not correct. So that's how you double check if your unit vector is correct.